This is video 4 of a 4-video playlist on magnetic braking. In the previous videos, we derived a differential equation. In fact, it's this differential equation here. And we stated that the solution to that differential equation was this here. We didn't show how we derived that solution. We did test it, so we're on firm footing, even though we haven't shown how to derive it. We tested and showed it works, so uh, you know, all pretty complete in our proof. But how do you actually solve differential equations of this type? We use a technique called the auxiliary equation. This is what you do. You take your differential equation and you look at the primes. This is x double prime. You convert that into d squared, where d is just some variable name. You could use k squared. In fact, in most books they use k squared, but I've always used k for something else here. So I'm going to use d squared as my unknown. And the program actually remembers how to do that. So rather than type it in, I can just go here to one of my derivative operations and convert all my derivatives into unknowns. Let me go back and look at that one more time. This double prime is going to get converted to d squared. This single prime is going to get converted to just a d, and the k is just carried along for the ride. So there it is. That's called my auxiliary equation. Now I solve that for the unknown d. What are the roots of this equation? In other words, what values should d take on to make this equation true? Now, in this case, it's a very simple equation to solve. You just factor it. So let's see, factor all terms, and we see from this that the two roots of this equation are d equals 0. That's what you get when you plug 0 into this value here. That's the left-hand side becomes 0, so that's one root. And the other root is to let d equal minus k. If you plug minus k in there, then the left-hand side becomes 0. So those are our two roots to that equation. And what do we do with them to get our solutions to the differential equation? We take those roots and plug them into this exponential formula. So plugging the d into this exponential formula, it's whatever the root is times t, and since this root is 0, the x of 0 is just 1. So one of our solutions is a constant. And if you look back up here, it's pretty clear that that's the case. If we plug a constant into this formula, we differentiate it once, it's going to go to 0. If it doesn't depend on t, its derivative is 0. So certainly if we differentiate it twice, it's also 0. So this thing definitely is solved if we plug in a constant. Now our second solution, we take the k, which is our root, and plug it in this spot here in front of the t, and that's also a solution. And we can test that by just applying the differential equation to it. So, all right, so let me big this. Let's just take a look at that. Let's get rid of our little helper there. If I apply this differential equation to it, it says differentiate it twice with respect to t. That's going to throw out that k twice, so I end up with just a positive k squared in front. And then if I do this part here, I differentiate it once, it's going to throw out a negative k in front, but it joins up with a k I already have there, so that gives me a negative k squared altogether, and so they cancel one another. Now the program has the ability to just apply this differential equation automatically, and it does so fast you don't see what it's doing, but that, I trust the program. It's done this 1,000 times, so that's proof enough for me. But let's, is there some way to show that with a little more detail? Let's change this k temporarily to our unknown d. Actually, I want to make it not k. Remember, d is minus k, so I have to put that d in there. Okay, what am I doing here? Okay, there's the d. If I do that, it won't collapse immediately. We can get a better idea what's going on. So d is minus k, but it won't immediately collapse. Let's apply my differential equation and see what happens. So if I use that d in there, I apply it, the differential equation twice, that's this term, it throws out that d squared. And d in there comes out as a d squared. Here I apply the differentiation once, it throws out only one d. And it had a k that is part of the equation. So you can see why this is going to work now. Let's actually factor all terms here. Notice what happens. We get our equation here. This e dt is a positive number, so we can actually divide that out of the equation. So if I t that up and divide, that's no good. That's no good. I gotta be a little more careful. Let's t that up, and then I divide. I get this equation here. Notice that that's our auxiliary equation. That's this thing down here. So that says that if I can make this thing 0, then my differential equation will be true. Let me go back one more time. That's what our differential equation becomes. Let's go back even further. This whole thing is our differential equation with d not specified as minus k yet. But if we factor that, we get this part here, k plus d times d. That is our auxiliary equation. So if we find a root for the auxiliary equation, this side will collapse to 0. And then finally, any linear combination of these two solutions will also be a solution. That's why we express our general solution as C1 times 1, which is just C1, plus C2 times e to the minus kt. Now, we're done. That's how you derive it using auxiliary equation, but let's finally just test it one more time. So if I take this thing and big it, if I apply my differential equation to this, it should come out as 0 equals 0. And the program again knows how to do that, and it does. So again, I trust the program. I could do it by hand. I get the same thing. Well, let's do it by hand. Let's one more time. Let's do it by hand as a test. Let's bring up the differential equation and just make those substitutions. For x double prime of t, I'm going to substitute that. And for x prime of t, I'm going to substitute that, and it collapses. So that's our derivation of the solution and our proof that the solution works.